Hello, welcome to another session. So today we're going to do the best topic in the whole high school syllabus for maths, and that's integration in the extension 2 4-unit syllabus. It's the best topic. So it's a topic where it requires you to build on the learnings that you had in 3-unit and 2-unit. But not only that, there's a few sort of parts of the topics where there's a few tricks, a few techniques that you need to learn. It's a great topic with lots of tricks and lots of techniques. So what I'm going to do, I'm going to do a 3-part series where I'm just going to show you a few examples with potentially a few tricks that you may or may not learn at school or on YouTube, etc. Some of these techniques and tricks can be used at school, but for some of them, you probably need to check with your teachers just in case your teacher wants you to show different types of working out, where the methods I'll show you can be faster and quicker, but may not have that level of working out. So best to check with your teachers before you apply these methods. So the 3 sessions I'm going to do, the first one I'm going to do is revolving around by parts, which is the core topic in 4-unit maths for integration. Next session is on trig, and trig has quite a diverse list of questions that you can get with different techniques, etc., from T results to trig substitution to just applying trig identities. And the last one, I'm just going to call it special cases and cool questions that you see in the syllabus. So without further ado, let's hit up the slides and start on by parts. So I'll start with the blank slide, where integration by parts is fundamental to this syllabus. And I know you're all aware of the formula at play. So by parts basically says if I integrate a function and I diff with another function that's attached to it, I get uv minus the integral of v du, and essentially that forms our formula. And what's important here is, a few common, when do we use by parts? The most common examples, maybe I'll write the words common examples. To apply by parts would be when there's sort of dual functions in the same sort of expression. So if I have x, ex, dx, and when you hit a wall in terms of, so the first thing you should ask yourself there when you see this in the 4-unit paper is, can I use substitution or u sub, right? In this case, because the function on the exponential, if I differentiate x, I don't get x. So that it doesn't cancel out with the function in front. I'm stuck for substitution method. This is where integration by parts sort of works nicely because it's the product of 2 functions. The classic cases you get are exponential in algebra, maybe exponential and trig is a classic one, and maybe logs and algebra as well. So something like that, and we'll do a very similar question to this from the HSC today. So these are classic examples that you see in the by parts syllabus. So now, I was surprised to hear from a number of my students that teachers don't actually talk about the next acronym, the LIATE acronym. Now, basically, the acronym LIATE, so use LIATE, right, as an acronym to choose the substitution for the u function, right? Now, I was surprised to hear that a lot of teachers don't use this because this acronym is such an easy way for you to remember because you got to choose 2 things, right? In your question, you got to let u be a function and dv be another function where you're going to differentiate and dv you're going to integrate, right? By using LIATE, it gives you almost like a systematic thinking pecking order, right? To choose the function for u. So where L represents logs, so that's, for example, ln x, right? Yeah, ln x, and maybe I'll just get rid of the ex, I'll just write ln x, right? I represents inverse functions. So your classic tan inverse or sine inverse x comes in here. Your algebra, and for all intents and purposes, algebra includes numerals as well. X squared, blah, 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 blah. Your t is trig. So obviously your sine x's and your cos 2x, blah, blah, blah. And last but not least, your exponential functions is last on this pecking order. So EX, E3X, stuff like that. Now, a lot of schools use this, some schools don't, and that surprises me, but a lot of schools, when they ask you to choose U, what they don't really tell you is why. Now, the reason why LIATE works well, ironically, it's actually not about the function of U. It's about dv, right? The other function, because by selecting these functions for U, you're actually inadvertently selecting the function for dv. Now, this pecking order from logs, inverse, algebra, trig, and exponential, if you think about the order that it sort of goes from left to right, right? It's actually the order of difficulty, the order of difficulty lessens when you integrate things. So for example, in exponential is probably the easiest to integrate. Trig, pretty easy. Algebra, pretty easy. Inverse functions, pretty tough. Logs, pretty tough to integrate. Now, what that means is by selecting logs to differentiate first, you're leaving dv functions to be easier to integrate. In short, the acronym LIATE gives you an order to select things that you can differentiate so that the remaining function can be easily integratable. Now, that's especially important because there are questions, and I might delve into some of these in my sort of special cases session where it's not obvious which one you let U, because the relationship, there might be sometimes only one function, in which case you don't know which one to choose for U, or the one that when you apply LIATE, it actually fails, right? The function that you use for U doesn't follow the LIATE formula. So I guess what I'm trying to say is LIATE is a good framework, but it doesn't work 100% of the time. Probably works about 75, 80% of the time. And the harder special cases that fall outside of LIATE are the other interesting ones in this topic. So I'll deal with that in a sec. But I mean, just to explore this a bit, right? So from these common examples, LIATE absolutely works. So if I was to choose U from all of these, now I know that from this one here, that falls under the algebra camp. That's the exponential camp. So if I had to select U to be one of these functions, I'll select A comes before E in the LIATE acronym. Right? So X there would be definitely my substitute for U. Similarly, in the next one, that's exponential. That's trig. So once again, E is at the end, so I would let sine X be my U. And last but not least, if I had algebra and logs, I'll definitely let logs there be my, that's algebra, that's logs be my function of U, right? So with that in mind, let's do a quick question on applying this, because what I really want in this session is to explore this technique of by parts, but using the DI method, the differentiating and integrating method, which basically knocks through these questions, which can take a long time if we apply by parts, and especially if there's a bit of recurrence in place. But the DI method is beautiful, and I'll explain when I get there. So for now, let's do a quick question from the HSC, 2001. Let me just zoom in for a bit, so I'll write a little bit neater. So example from the HSC 2001. Sorry guys, when I talk about this topic, I am pumped. This is my favorite topic in this whole 4-unit syllabus. It's amazing. It's one of the topics that hasn't really changed much between the old and the new syllabus, for good reason, and I'm quite happy with that because it's an amazing topic. So evaluate. So here we have a classic example. Now, just just the fact that it looks like quotient rule and it's a quotient instead of a product might throw people off, but we do exactly the same, right? We basically say to ourselves, well, I have logs there, and technically speaking, it's 1 on x squared. That's algebra. Yeah, so then off to the side, then I would say let my function of u be, because of LIATE, I'll let it be ln x. And because of LIATE, then the remainder, then in this case, dv would equal to 1 on x squared dx, right? Everything else in this expression here. Now, remember, and you know what? To make my next DI method conversation a bit easier, I'm going to just go for D and I here, where the D means that I'm going to differentiate, and the I means that I'm going to integrate, right? So differentiate that. So du equals to 1 on x dx. You can write that as dx on x if you want to. This side, now that's like x to the power -2. So I add 1 to the power minus. So simplifying all that, you sort of get like that, right? So I've got my tools to apply to the by parts formula, where the by parts formula, now remembering the limits here, equals to uv, so u times v, so it looks like it's negative ln x. It's poorly written. Ln x on x for an e minus, and it'll be v du, so there's a minus as it becomes a plus. Integral limits are still there. And this guy times this guy. So it's like 1 on x squared dx, which is nicely integratable or easily integratable. So let's sub it in. So you know what? I'm just going to reverse the limits. So this guy, these guys here, once again, whenever I say this to my students and they're like, well, we don't learn this at school, I'm surprised. Basically, whenever there's a negative, to make your substitution of the limits a bit easier, you can knock off that, get rid of that negative and flip the limits, right? Yeah, numerically, it's the same equivalent expression, basically, because you're subtracting the two limits anyway. If I get rid of the negative and sort of swap the limits around, it just makes my life a bit easier. So integrating this guy will be negative 1 on x for an e. Yeah. So subbing the limits there shouldn't be hard. Ln e on e minus ln 4 on 4. I think that looks right. So that's the first square bracket there. This one here would be 1 on 4 minus 1 on e. And then it's just a matter of cleaning it up and just keeping in mind that ln e is 1. So that looks like 1 on e minus, so that's 2 on e minus ln 4 on 4 minus a quarter. So technically you can put those under the same, that's it. You can put on the same common denominator if you wanted to, but I'm going to leave it there. So nothing too wow about that. Bit of limits involved there. That's a HSC question, right? I believe it's like about 3-4 marks, so decent value. Now, this is exciting. So if you've never seen the DI method, you're in for a little bit of a treat. The DI method allows you to do integration by parts, but it cuts out all the working out and gets you the answer pretty immediately, right? And I'll show you an example that uses by parts, and then I'll do it using the DI method just to show you how much time and effort you actually save. So I'm going to zoom in. I'm going to give you another question, right? Let's just do this, and I'll call it method 1 using traditional by parts methodology, and then we'll do it by DI method. So if I asked you to integrate this guy for me, right? It's a classic question, right? It's a classic question where, remember, if I use by parts, this guy here is algebra, this guy here is exponential. I would let u equal to the algebra component, and I would let dv equal to my exponential component. All pretty straightforward thing, process. And once again, just for my purpose, I'll put a d and an I here to remind me to differentiate and to integrate on this side. So differentiating this guy, I get du. Bring down the 3. And integrating ex is ex. Beautiful. Got my tools. Let's sub it in now. What you'll sort of find, right? Maybe can I ask a favor. I'm just going to call this capital I, right? Because there's going to be a number of steps and iterations or recurrence. Yeah? Just makes life a bit easier. So I equals to UV, subtracting du, v du. So maybe I'll bring up the 3, integrating x squared x. Now, you're starting to get this process of recurrence, right? Because stepping from there to there, x cubed's gone down to x squared, but I still need to do by parts again to basically integrate this thing. So I'm going to set it up again, right? So bear with me while I do this, because I just want to demonstrate, right? And what it means when I use the DI method, what sort of time saving am I getting here, right? So once again, let u equal to the algebra component, and let dv equal to the exponential component. So once again, differentiate, bring down the 2, dx, v equals to ex. Got my tools once again, and just to be extra clear, this algebra part that I'm doing, sorry, this by parts part is just for this integral here, right? So everything else sort of stays the same, all good. Minus 3, and then in here it'll be u times v, so x squared ex, subtracting the, I'll take out 2, and then it's x ex dx. And once again, I need to apply another layer of by parts to this. I believe I'm almost there. So once again, let u equal to x, let dv equal to ex dx, du equals to dx, v equals to ex. Okay, almost there, guys, almost there. So maybe before I actually do all that, I'll do a bit of expansion. So ex minus 3x squared ex looks like it's plus 6, is it? Yep. Of this integral, in which case I'm just going to hammer out the by party. So uv subtracting the integral of ex dx only. Good. So for that last step, I don't need by parts anymore. I can just integrate ex because I know that's just ex. So my final answer, I say final, I'm just going to factorize that at the end just to clean it up. Let's have a look. Plus 6x ex, and then minus 6 integral as ex plus c. You know what, I'm going to leave there. I was going to factorize the ex from all of those, but yeah. So that's my answer. Now, hopefully the feeling you got there was, man, that took a while just going through that process of by parts a few times. You know what, I'm going to get a red pen up. I'm going to call this guy method 1. Right? Method 1, traditional by parts. Now, I'm going to do this method 2 over here. Yep. So watch this, right? This is going to be amazing. So, and DI method works especially well when there's a bit of recurrence. And what do I mean by recurrence? Basically, there's multiple steps of by parts, right? So this question here sort of says I equals to, the original question was x cubed ex dx, right? So in setting up the the DI method, you basically draw almost like a mini table, right? Mini table with 3 columns, where the first one here, so this middle column here, D and I, right? DI method, where the D stands for differentiate. So let me just write that. You don't need to write this all the time, but it's just for me to remind you, right, what the DI stands for. And then do me a favor. Once you draw this table, can you please put a series of plus, minus, plus alternating, right? Minus. I believe we need about 5, right? Let's just do about 5. Now, this is the cool part, right? This is the cool part. So basically, if your question is x cubed ex, right? I want you to put that question here, where just like your LIATE methodology, this is algebra, so I'm going to differentiate that. This is exponential, so I'm going to integrate that, right? So you put the x cubed here and the ex here, right? Just like how this is like your u, and this is like your dv, right? So maybe I'll put that up here. This is like u, and this is like dv. Yeah? Now, once you do that, this is all you do. In this column, you basically just differentiate as you go down, right? So watch this. X cubed, 3x squared, differentiate that, 6x, differentiate that, 6, differentiate that, 0, right? All I've done, step by step, is just differentiate. On this side, all you do, step by step, just integrate. The beauty about EX is it just keeps integrating to the same thing. Yep, beautiful, boom, 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 boom. And this is the fun part, right? So this is what you do for your answer. To get your final answer, you basically go, follow the positive goes over here, and then you go diagonally, boom, across, boom, across, boom, across, boom, and technically 0 times something, but because it's 0 times whatever, you don't really need that whatever. Like you can actually do it again if you wanted to, where you can add an extra EX if you wanted to, adds nothing. Now, your answer, I equals 2. You follow the red, right? So positive x cubed EX, sorry, don't even need the integral, x cubed EX minus 3x squared EX plus 6x EX minus 6EX plus 0. I'm done. Let's compare. Done. Exactly the same answer, but super quick. This method is amazing, right? It's such a neat way of doing integration by parts if there is recurrence. Now, if there's no recurrence, if you do like the last question, do it in one step, both methods are approximately the same. In fact, I would do it in the traditional way because there's more working out for your teacher. But if there's like multiple layers of integration by parts, hammer it out with the DI method. Yeah, hammer it out. Now, how about just to really hit home this concept, let's do one more. Right? Let's do one more using the DI method. So if I asked you, let's see, let me flip back to my example color. Zoom in. So if the question says example, evaluate, right? It works especially well when there's like, you know, some sort of big polynomial, and trig and sine and stuff works really good, or exponential. So maybe we'll do a trig one because we did exponentials just then. This is nice. So you can imagine, right? Because if you let u equal to x5, you're going to go x5 as u becomes x4, x3. You're going to do it by parts like a few times. But now let's set up our by parts. Yeah. So let's set up our DI methodology. Right? So I know this is D, this is I. Now, maybe if that's x5, I'm expecting at least 6, so minus, plus, minus. The table's not big enough, that's fine. Minus, maybe I'll do one like that. Let's see how we go. All right, so zoom out. Remember, this is your original question, and that goes here, right? Now, you would have let u, this guy here is algebra, this guy here is trig, LIATE, A comes before T, so this guy comes into your differentiating column, this guy comes into your integration column. Yeah, so we have everything set. Guys, differentiate this downwards, so 5x4, put down the 4, 20x3, 60x2, maybe I don't have enough, let's see, 120x, 120, and I'll put an extra 0, right, and I'll put an extra plus there, not that I need it, but it's because it's 0. All right, that was fun. On this side, now, integrate, just be careful, right? Someone told me, when you're integrating trig, if you remember this for me, you sort of rarely do it wrong. So someone told me that sine integrates negatively. That reminds me that when I integrate sine, it's going to be negative cos. But if I integrate cos, it's going to be positive sine, right? That little acronym works really well. So look at this, integrate sine, negative cos. Integrate cos, positive, but that already has a negative, so negative sine. Integrate sine, negative cos, already got negative, become positive cos. Integrate cos, positive sine. Yeah, sine integrates negative cos again. Yeah, and then you can sort of see repeating, right? Yeah, so it becomes negative sine. And I'll do one more. Negative sine becomes positive cos again, right? Perfect. I've got my LIATE, sorry, I've got my DI method set up, right? So let's do this, right? So positive with this guy diagonally. Negative with this diagonally. This guy diagonal. This guy diagonal. This guy diagonal. This guy diagonal. And the 0, not that it matters, but let's just do it for completeness, if anything. And here's my answer. So therefore, I equals to, right, follow x5 times this, so negative x5 cos first, right, to kickstart that, minus, so when you times a red, there's a minus times a minus, that's plus, right, plus 5 x4 sine. Next one, positive 20x3 times cos, that's plus 20x3 cos, minus 60x squared sine, so 60x squared sine, plus 120 minus cos, so minus 120x cos, minus 120 minus sine, so plus 120 sine, and then 0, so plus, so sine x plus c. That is my answer. Pad box. That is my answer. And that is the DI method, right? Saving you quite a few a lot of time. I mean, if you were to do this by traditional by parts, it'll take you a while just to set up UDV, etc., right? And then multiplying out, this just hammers it out so quickly. Can you use this in the test at school? Can you use it at school? Don't know. Ask your teacher. But if you can, definitely try to apply it if you can. Now, if the by parts question requires you to do it in one step, and that's it, use traditional. But if if there's multiple recurrent steps, DI method hammers it out so quickly. Hope you guys enjoyed that. If you did, can you please give me a like? Tell your friends. If you haven't subscribed, please try to. I'll keep trying to churn out a bit of content for you, especially in this topic where I want to give you some of the cooler questions and cooler techniques like this. Next week, my favorite all-time integration question in the trig subset of the topic. So I'll see you then.